As we talk about biodiversity and loss of biodiversity and threats to biodiversity, extinction is one of the major processes that contributes to overall biodiversity. If we think about it, the number of species we have on Earth today is the difference between speciation, how many new species formed, and extinction, how many we've lost. So extinction becomes a big piece of this equation. Here we'll take a brief look at extinction. This figure shows us that we've had major extinction events throughout Earth's history. We saw a large extinction event at the end of the Ordovician, at the end of the Devonian, end of the Permian, the Triassic, and the Cretaceous. We do see that there's sort of a cyclic phenomenon where we see a massive extinction event, which is followed by lots of speciation, because now that we've had all these extinctions, there are niches to fill, and so we get new species forming, and then over time we get another extinction event, and then another massive speciation event. So we see these cycles throughout time. So we call these mass extinctions. And we've seen 5 of these mass extinctions throughout Earth's history, and we can tell this from the fossil record. And it would appear that we are currently in a 6th major extinction event when we look at extinction rates today. So let's compare the extinction rate today compared to what we call background extinction. This dotted line here represents background extinction. This is sort of what we would expect the natural extinction rate to be based on history. And then these other lines are representing the estimate of the current rate of extinction. And we have 2 different sets of curves there. One is based on a very conservative estimate of the current extinction rate, and the other one is somewhat less conservative. We can see that the conservative estimates show us a slightly higher extinction rate than what we see in the very conservative estimates. So if we're being optimistic over here on the very conservative side, this is what we see. And if we're being a little bit less optimistic, it's probably over here on this side. But it's probably somewhere in between. And in both cases, we can see that the actual estimated extinction rate is much, much higher than the background rate. And this is looking at vertebrate species that were recorded as extinct or extinct in the wild. Sometimes if we have one in a zoo, then we'll still call it extinct in the wild because technically at that point it is extinct. These are recorded extinctions. This graph that we're looking at over here is again using these 2 different estimates in the 2 different colors for different groups. This is asking if we had the background extinction rate, how many years would it have taken us to get where we are today based on these different numbers? So the actual time frame is 114 years. If we use our conservative estimate, we would say that it could have taken almost 6,000 years to get that many fish species to go extinct that we've seen go extinct in 114 years. If we use a slightly more conservative estimate, it's closer to 2,000. So anywhere from 2,000 to 6,000 years it would have taken, but this is what we've seen in 114 years. And look at it for amphibians. Fish are about the same for the very conservative estimate, but for the conservative estimate, they're saying it should have taken about 10,000 years to get that many extinctions that we've seen in 114 years. So with all of these, we can see that it's highly elevated, anywhere from 2,000 years on up to 10,000 years, what we have seen in 114 years. And then over here, we're just seeing estimates of what percentage of species in these different groups are threatened with extinction. And we can see that we have lots of different groups of organisms that have very high percentages of species that are threatened with extinction. Here we can look at just a few examples of species that we have recorded extinctions for in relatively recent time. We had the dodo bird that was hunted to extinction around 1662. The Steller sea cow was discovered by Europeans in 1741. There were large numbers of them. They were hunted for meat and oil and became extinct 1768, only 27 years after discovery. Passenger pigeon. The passenger pigeon had huge populations, single flocks in the order of 2 billion individuals. The last passenger pigeon died in 1914 in a zoo. So this was a species that was highly abundant and then was hunted to extinction. The last penta giant tortoise, Lonesome George, from the Galapagos, died in 2012. The splendid poison frog from Panama was declared extinct in 2020. Now, some of these, when they say declared extinct, the last wild sighting for the frog might have been in 2014, but then they weren't declared extinct until 6 years later. So sometimes there's a lag in when they're declared extinct from when they've been last seen. Spix macaw from Brazil was declared extinct in 2016. the western black rhino back in 2011, and the Yangtze River dolphin in 2006. So this is just a few of the extinctions that we've seen in relatively recent times. Now, how do we estimate extinction rates? We need estimates because we don't have direct observation. Direct observation is going to be very difficult to get. We can't really watch all of the extinctions. Keep in mind, we've only described, 20% of the species on Earth. So how do we know that species are going extinct when there's species that we've never even seen or described that could go extinct before we ever do see them? We need a way of estimating what that extinction rate is. Now, the background extinction rate is listed as 1 extinction per million species years. So don't get too caught up with exactly what that means. It could be that you have 1 species going extinct every year for 1 million years. You might have in 1 year 1 million species go extinct. It doesn't really matter exactly. Don't get too hung up with exactly what that metric means. Think of it more in terms of a comparison. So what we want to do is to compare this background extinction rate to what our current extinction rate estimates are. Now, there's a couple of ways that we can estimate extinction. One of the ways we can do it is we can estimate based on the extinctions that we've seen since 1500. What documented extinctions have we seen? If we base it on extinctions that we've seen, the current estimates are anywhere from 26 to 100 extinctions per million species years. That would indicate that it's anywhere from 26 to 100 times higher than the background extinction rate. When they run these predictions to the end of the century, they come up with a number that's around 1,500. So that would mean that if those predictions are accurate, by the end of the century, our extinction rate is 1,500 times higher than the background extinction rate. Now, another way that we can estimate extinction rates is based on the species-area relationship. Remember, the species-area relationship essentially looks at the species area curve that we see here. The idea is that larger areas are going to contain more species than smaller areas. So if you think back to island biogeography, the bigger the island, the more species. We can use the species-area relationship to try to estimate the number of species that we would lose when we destroy habitat. Remember, habitat destruction is one of the major causes of loss of biodiversity. If we're going to reduce the size of a habitat, how much will we lose in terms of number of species? We can see from here, if we were to go from 100, we have almost 100 species, let's say up here, down to 10, now we're at about 50 species. So we've reduced the number of species by 50% by decreasing the size of that habitat. Then what they'll do is look at what are the estimates of loss of habitat. And again, these are estimates. We don't know. It's not like somebody calls up and reports, hey, we just cut down 40 billion acres of rainforest today. Nobody reports those numbers, so we have to estimate these. But based on estimates, then the current rate of species loss is anywhere from 5 to 1,000 extinctions per million species years. These are estimates, but if we look at how this compares to background extinction, we're looking at somewhere on the order of 500 to 1,000 times higher than the background rate. So that means that we are currently experiencing and will experience mass extinction.